Hello, everybody, and welcome to this fourth keynote of the 16th OpenFOAM Workshop. I'm delighted to welcome a colleague of mine from the School of Mathematics and Statistics in University College Dublin, Professor Frédéric Diaz. So Frédéric today is going to talk to us about impact pressures. So I'll invite you, Frédéric, to turn on your camera and to share your screen. And we have 30 minutes for the session, and if we have time at the end, then feel free to put your Q&A in the live Q&A section, and I can read out the questions at the end. Great, thanks very much, Frédéric.
Good afternoon, and first of all, thank you, Philip, for the invitation to give this talk for this OpenFOAM conference. So I am a numerical user, not necessarily of OpenFOAM, but so today the purpose of the talk is more, to present some interesting problems from the numerical point of view. And so I want to talk about slamming. And so most of what I'm going to cover today actually is in a review paper in the Annual Review of Fluid Mechanics that came out in 2018. Co-authored with Professor Guidalia from France. But at the end, I will show some recent results. So what is slamming? So slamming is the violent impact between a liquid and a solid. There are a number of applications in shipbuilding, in aeronautics, in the liquid gas industry. That's the industry with whom I collaborated on this topic, also on marine renewable energy, and also in ocean engineering. And that's something that I am doing now in a more recent project. So going back to the example of the liquid gas industry, so this is an illustration of a tank of an LNG carrier. So just to give you the an idea of the size, you see a human being at the bottom. So typically it's 40 meter by 40 meter. So this is filled with liquid gas, and then the LNG carrier goes across the oceans and sometimes hits some storms. And so there is some sloshing and also some slamming can occur. And this is an example of some damage that was done on a ship. So essentially we can decompose these type of impacts into three idealized problems. The first one is well known in the shipbuilding community. That's the Wagner problem, and it's like a ship hitting the water surface. So here's the example. The body could be the ship, for example. Beta is this dead rise angle between the solid boundary and the free surface. And V is the velocity at which the body goes down. So then the estimate that Wagner got in 1932 for the maximum pressure is 1/2 coefficient Cp, which is defined here. And as you see, when the angle beta goes to 0, this becomes very large. And then times the density of the liquid, here water, times this velocity square. The second one that was developed in the context of breakwaters by Bagnold and later by Mitsuyasu. And so this example can be summarized like this. You consider a solid boundary or wall with some gas, but then it's entrapped between some liquid which is falling against the wall at a velocity v again. And so then there is this expression to find the maximum pressure. And because there is the gas here, we have to use compressibility of the gas. So gamma is this index. And so this is the equation. And then there is this impact number, which is the liquid of the mass of the liquid times the velocity square of the liquid divided by twice the initial pressure P0 times the initial volume of the gas pocket here. And the last one, even older, which is well known for people studying shocks, it's the Rankine-Hugoniot example, and here it's represented as some liquid impacting another liquid and then the wall, but then the liquid here is considered to be compressible. And so the maximum pressure is given by P0 plus the density of this liquid initially, plus times the velocity again, times the speed of sound. And then the error here is in terms of the Mach number. And then there is the shock speed A, so the shock coming back. So it turns out that these three type of impacts occur in this slamming problem. So here are some experiments that were performed. And so essentially the experiments were a wave impacting a vertical wall. And so then and here are some recordings of the pressure along the vertical wall. And so you see that depending on how the impact occurs, the signal can be different, but we see all of them. So the ELP1, elementary loading process number 1, which is the one corresponding to the compressible liquid, actually happens when the tip of the jet hits the wall here. That's what we call the direct impact. Then the second one, ELP2, that's this peak here. And actually this one can be explained only with incompressible flows. And it comes from the jet impacts. So earlier that was the ELP1, but now there is a change of momentum and the liquid now goes quickly along the wall. And it's this change of momentum that creates this pressure peak. So that's the ELP2. And then the ELP3, which you see here with the oscillations. And that's when the entrapped gas pocket oscillates. So you get these oscillations. Okay, so when you want to study this slamming, there are several mathematical models that you can use. From the most general one, which is the Navier-Stokes equations for the 3D flow of two immiscible compressible fluids in the presence of surface tension. Then average models, where the Navier-Stokes equations now are for the volume fractions of gas and liquid. And so this is used when the geometry of the interface is complicated. Then there are the compressible aerated flow models, where the aerated fluid is a homogeneous mixture of incompressible liquid and compressible gas. The difference between the two is that there is only one velocity field as opposed to this one. And then the incompressible fluid models, one or two fluid formulations of the unsteady incompressible Navier-Stokes equations with an interface and a turbulence model. And then one special case, of course, is the potential flow. So the key question is, it's a scaling issue that at least, for the LNG people, and that's why we started working on this problem. And so assume that the ratio of the full to model scale is lambda. The simple question, how do the slamming induced pressure scale? So what is the ratio between this maximum pressure at full scale divided by the model pressure? So obviously in hydrodynamics, there is an important dimensionless number, which is the Froude number, velocity divided by square root of GL, L a characteristic length. And so preserving the Froude number at both scales implies that the full scale velocity then is square root of lambda times the model velocity, and the full scale time is square root of lambda times the model time. So, but for the pressure, then actually then it gives a ratio lambda. But now for the problems involving compressibility, so the Bagnall and the Rankine-Hugoniot, the solutions are based on the fact that the same gas is used for the full-scale prototype than for the model, or at least that both gases have similar speeds of sound. But in practice, the compressibility of the gases and liquids then is not adequately scaled at both scales, and so that's what we call partial Froude scaling conditions. So this is the case when the fluids remain the same at both scales. In that case, there are gas and liquid compressibility biases that spoil the Froude similarity. If, and we can do this numerically, if the compressibility of the gases and liquids is scaled according to fluid scaling, then the pressure scales as lambda as well. And that's the complete fluid scaling that we can accomplish numerically, but not experimentally. So just to illustrate this example of bias at small scale, so locally the impact process is not similar for similar inflow conditions. So this is at scale 1, and I represent the liquid by this mass here, the gas by this spring, and then the wall. And then if with the right compressibility scaling, with a complete fluid scaling, then we would have, you know, the liquid scale back to this, the gas to that. But because if we cannot scale the compressibility, then this is the bias which is introduced here, a compressibility bias. So, but I showed 3 models, and the biases are different from for different impacts. So this is summarized in this table here for the 3 elementary loading processes. So the direct impact, and for that one, the scaling is square root of lambda. For the Wagner type, which is incompressible, then it's easy, it's lambda everywhere. And then for the gas pocket, there are actually 2 different cases, but so then we can distinguish between weak impact, moderate impact, and strong impact. All this is explained in that review article. So now talking about the numerical solutions, so essentially there are, you know, how do you represent the interface? And here I put 4 ways to do it. So the interface must be found as part of the solution that's used in potential solvers. The level set method is one option. The hybrid Lagrangian method is another one, and the volume of fluid approach is a classical one. It's easy, but diffusive. Of course, you know, this is a brief summary, so one has to be careful, but to generalize, but that's the overall impression. Local conservation laws. So for the most general system, for the compressible multi-phase flow solver, my colleague, Professor Guidalia, has developed a cell-centered finite volume platform, Flux IC. And with that method, the fluids can be separated by a sharp interface. For the average models, the one issue is that nothing guarantees that exact Riemann solvers exist, and the convective part of the average models might not be hyperbolic. And then for the incompressible Navier-Stokes equations, of course, you know, there is fluent OpenFOAM, star CCM. Now, I have to say that, of course, you know, this slide is probably, you know, a few years old, and these continue to evolve. So now I know that there is some compressible solvers also within OpenFOAM. So this has to be updated on a regular basis. So now let me go to the 3 applications, actually 2 because of lack of time today. So I will talk about the liquid impact on the wall, and then the slamming of wave energy converters. So for the liquid impact on the wall, so these are some experiments that were performed in the Netherlands. And so essentially there are 3 types of impact: the slush, and you see how the free surfaces when it hits the wall, then the flip through, which is a limiting case, and then the gas pocket. And you will see an animation now of this gas pocket when it hits the wall. So this is, now there are all these pressure sensors, P1, P2, P3, up to P8. That's the pressure signal for the first one here. And then for the flip through with a very large peak here, this is the largest one here. And then for the gas pocket, these typical oscillations behind. And there are also some instabilities present in the gas pocket. You actually see it here. So 2 fluid models are necessary to simulate such instabilities. This is a hot topic right now. One slide here, the comparison between the compressible and the incompressible case. Again, that's this wave hitting the wall. And so this is here using Garris. And then that's hybrid model using both Garris and then Flux IC to deal with the compressible effects. And so what we see is that the pressure peak arrives earlier for the incompressible case, and the amplitude is smaller. I will skip that one. That was a benchmark we prepared. So I will go now to the slamming of wave energy converters. So these are some experiments that were performed at Queen's some years ago when we were studying this wave energy converter, the Oyster device, which is a flap that oscillates back and forth in the waves. You will see the animation soon. Actually, I will send it now. And so this was a 3D experiment. There were 13 pressure sensors on one side of the flap, a modestly high-speed camera, and then we generated both monochromatic and polychromatic waves. And so you see the slamming that occurs, so this violent impact of the flap back onto the water surface. So when we did this first experiment, we were, well, we didn't know where to start, because first of all, for visualization in 3D, it's not so easy. And then, you know, it's hard to see because there is both the emotion of the flap, then the impact. So as opposed to a problem where the boundary is fixed, even more complicated. So then we decided to go, we went through 3D, from 3D to 2D. That's unusual, usually it's the opposite. So we did some 2D tests at École Centrale Marseille with a 40th scale model of this flap, and the flap now was spanning the width of the flume. So then there were these pressure sensors again, and also immersion gauges in the front and in the back to get the water level. And so now this is, we see better what happens in 2D. So that's the flap coming back, and then this slamming again, and then this the generation of this jet. So we wanted to, you know, to try to use the elementary loading processes to understand this. It's mostly dominated by Wagner, but there is definitely some compressibility effects as well. So this is an example of the pressure plot. So as a function of time, and here that's the distance from the hinge, and then the red, you see the high pressure that propagates, goes up along the flap, and that's the water level here. And then these oscillations are genuine here due to some bubbles that are present. So these are some numerical simulations. So what you have is in black, these are the experiments. The wave comes from the left, and then it's A, B, C, D, E, F, G, H. So we have first the flap which is being pushed, then it goes back up, and then it starts falling back, and then that's when the slamming occurs. And these are some comparisons for the velocity field. The color code is here for the velocities, and there was a pretty good agreement between the experiments. And there are some other things that we compared that I'm not showing here, just to save some time, but this is just to show a comparison. So I want to finish now with one of the things I'm working on, which is no longer with industry, it's with nature. And so I'm interested in the motion of boulders on tops of platforms. So this is now the sea here, the sea bottom, a vertical wall, that's a cliff, and then a boulder at the top. And so in the past, people have distinguished between breaking wave impacts, where the water level essentially goes like this, and then the wave hits, and then there is this initial spray, then the overtopping spray, and then this return flow here, and well, it generates some very high speed flow. And then the non-breaking wave impact, the water level is much higher, almost at the level of the cliff, and so then suddenly it overtops, but then the water depth becomes much smaller, so the velocity is much higher, and so there is a fast bore coming from the collapsing surge. So we still don't know why these boulders move. We know that they move, so this is some evidence on the Aran Islands, here in Ireland, and so there is this photo of this boulder here. And then the in 2013, well, Rona Cox, a collaborator from Williams College who comes to Ireland every year, knows all these boulders, so she has a catalog and she comes in the summer. So this is this boulder in the summer of 2013, 128 ton, 14 meter above the high water mark, and 15 meter inland. And then she came back the winter after that, and the summer after that. That was after the bad winter of 2013-2014, storm after storm. And this is the same boulder, and you see some white here, and actually there is evidence that it moved by almost 8 meters. So this is the last slide here, so there will be time for questions. So these are some experiments we are doing now. The first set of experiments was done in February this year in Marseille with the collaboration of Olivier Kimoun, and then a new campaign is going to be done in a couple of weeks. And so here, actually, these are some numerical simulations that mimic the wave tank performed by Professor Shi from Cardiff University. And so actually, it goes again, you see the wave maker. This is all numerical. That's a blow up of the wave maker. That's the tank, the full tank. And then that's the boulder that we put on top, which is what we call a smart boulder, because it has accelerometers inside and a pressure transducer. So then it's here, and then we create this wave. And so now here's the, and if you look carefully, then you will see that the boulder has moved. So now, having the smart boulder, we know exactly the accelerations, we know the pressure at impact, and we obviously have this very high-speed camera as well, and we also have PIV. So you can imagine that we have a lot of data that we are looking at right now, and there will be more in a couple of weeks. So just to summarize, so for the slumming problem, there are various mathematical models of different levels of complexity. The incompressible flow models are okay for loading processes that food scale. For if you have bubbles or droplets, average models are okay. In all the other cases, compressible multi-phase flow models are needed. We have asymptotic solutions. They are useful to explain the observed impacts. Sometimes a succession of loading processes occurs, and the loading processes cannot be simply added. For the numerical solutions, each model has its strengths and weaknesses. A recent way to do it is to couple different solvers. So I call this the hybrid solution. CFD cannot be used to assess impact pressure during slamming. The CPU time is 10 to the 4th larger than the real time, but the CFD analysis are useful to identify the type and nature of impacts. For the experimental techniques, so they are still used for the study of slamming because it's so complex. The variability of local pressure measurements during liquid impacts is paramount, and the wave shape before impact can be reproduced very precisely, but repetitions lead to large discrepancies. Here's a list of collaborators, so I will skip this, and so from various places. And I just want to finish by advertising for a 2-year postdoc position here in UCD on a joint SFI-EPRSRC project. The UK investigator is Ton van den Bremer from Oxford Universities, and this is on breaking waves and crossing seas. And the main goals for the postdoc based in UCD will be to perform a systematic parameter study of maximum steepness and of the energy dissipated during wave breaking through numerical simulations. That will be done with our home code using the boundary element method. And I will stop here. Thank you.
Great. Thanks very much, Frédéric. Very impressive talk. In particular, the experiments seem like they throw up many mathematical modeling challenges, but also very many numerical modeling challenges. They're all very difficult to model. So we have questions coming in the Q&A, so we can go through those. I know I have questions myself, but I'll go through these ones first. So Lionel asks, I guess you used volume of fluid for the simulations shown, and which solver did you use? I guess he's assuming you're using OpenFOAM, but I'm not sure that assumption is correct either.
No, so you know, I think in the whole presentations there are probably 5 or 6 different solvers that have been used, and also especially, you know, that's the part I didn't present. We also design a numerical benchmark. So at the end we had, I think, more than 12 competitors. So some of them were using OpenFOAM, but you know, all types. So Fluent was used, and then some homemade code. So a whole list.
Sure. So all of the methods maybe is the answer. Let's see. One of the voted up ones. What software and what solver was used for the simulations in slide 22, if I remember correctly? So a related question.
Okay, so let me. So slide 22. Oh yes, so that one. Oh, okay. I don't see it, so.
Oh.
Well,
is it it's the end of the slideshow? Is it if you skip by?
Yeah, I don't know. Okay, so let me. Well, I just show it like this.
Yeah.
So that was that one was Fluent.
Okay. Very good. Let me see. Are you thinking of any application for the simulation of boulder displacement?
Yes. Well, so the application is actually on the okay, so why it's not okay. So oh yeah, so when I click on the, okay, so I will just show the slide like this. So yeah, these, you know, this is ongoing presentation, ongoing work. And this is, you know, being, you know, yesterday I had an email with Professor Shi from Cardiff. So this is ongoing work. So I just showed it here to say that we are doing it, but we are definitely mimicking these experiments with the numerical code of Professor Shi. So if you, he has written a lot of papers recently. So if you Google his name, and you can find some of his papers to have more information about the method that he uses.
Great. Is there any other factor that could have affected the location of the boulder? Is a question.
That could have affected
the location. So is there any other reason the boulder might have moved that is not, it's not just a wave impact? I think that's the question.
Yes. Well, you know, with all these investigations, you know, this careful catalog we have, you know, now we know that, you know, it's the storms that have moved most of these boulders. By the way, we just had a paper that came out yesterday showing that some of the examples where people claimed that it was tsunamis that moved boulders, we reanalyzed them and we claim now that this was storms. But still, that's a wave. But, in terms of waves, it's either storm waves or tsunamis. And I doubt that it's a human being, moving these boulders.
Yeah, sure. Hopefully it's not the people of the Aran Islands get bored in the wintertime and go down with a tractor or something. So very good. Could you comment a little on the effect of turbulence modeling on the liquid, the water breakup, for example, RANs versus LES or other methods?
So for the breaking, no, because this is ongoing work. So, but in one of the papers on the wave energy converter, we actually tested 5 turbulence models, but at the end there was not a, we selected one as the so-called the best one, but it was not major differences between the 5.
Okay.
So. Whoever asked the question can send me an email and I will send the paper.
Sure. Okay. Then the last question we have in the Q&A from Kent. Wave energy flap problem seems quite interesting. Was this done using a 6 degree of freedom solver, or was the flap motion enforced or prescribed as a boundary condition?
No, so the flap moves because of the wave. Okay. So then, it.
Okay, so it's part of the solution. It's one of the unknowns. It's calculating this. Very good.
But I have to say that this was definitely when we wanted to model this, I contacted several experts in numerical methods and say, this is really a hard problem. Can your method do it? Can your method do it? And the answer was, some people said no, because when you have something that moves more than 60 degrees, it's just too difficult. So we spent a lot of time before making it work. So I had a good PhD student, and he was using Fluent. So that's how.
Yeah, I can imagine even just the fluid mesh degradation.
Yes.
You need something special to deal with that, like overset or immerse boundary or something. So, and never mind the stability of the 6 degree freedom solver. Very good. Thanks very much. For a couple of minutes over. So it was a very nice talk, Frédéric, and thank you again for it.
Thank you.
Great. And okay, I'll bring this session to a close, and I think the next session, which is a training session, starts in a couple of minutes for everyone. All the best.